Welcome to chemistry class. In previous video, we have seen crystal field splitting, crystal field theory main postulates. Now let me see crystal field splitting. How the splitting will be there in d orbitals. Crystal field splitting as well as crystal field splitting energy or crystal field stabilization energy, like that it will be there. First, what is crystal field splitting? In crystal field theory only, we need to know first the splitting. What is the splitting? Let us see. So generally, d orbitals in the central atom. Remember, d orbitals. Main d orbitals are responsible for formation of complexes. The main concept of crystal field theory is d orbitals are responsible. So the d orbitals of a central atom, first they contain lowest energy. 5 d orbitals will be there. These are the, suppose if I take, this is energy order like this. If I take, this is energy of d orbitals in a m in the absence of, in the absence of ligands, in the absence of ligands. When ligands are not there, only central atom is there, metal atom is there, or metal ion is there. The 5d orbitals of m will contain lowest energy. When the ligands approach the metal, suppose this is a metal, you know, when there are no ligands here, the energy will be less. Like this, it will be there. When the ligands approach the metal, then the energy of d orbital increases. They will be get excited. The d orbitals of metal will be get excited. Means when the ligands are approaching, the energy of d orbitals increases. Means d orbitals will be excited. These are the d orbitals in a excitation. When ligands are approached. When ligands are approached. When ligands are approached, the energy of d orbitals will be increased. Energy of d orbitals will be increased when the ligands are approaching the central atom. There are no ligands, then energy of the d orbitals is less. When the ligands are coming, energy will be increased. So after approaching, when they are come close together, once again they are coming close together, then by this excitation, over excitation, and by the different orientation of these 3 orbitals and these 2 orbitals, different orientation of these 3 orbitals and 2 orbitals, they split into two groups. That is, some orbital in octahedral complexes, the splitting will be present like this. In tetrahedral complexes, the splitting will be there like this. Means Eg orbitals, these are Eg orbitals, will get higher energy than T2G orbitals in octahedral complexes. Octahedral complexes. When 6 ligands approach, Eg orbitals will get higher energy than T2G orbitals, they will be split. And T2G orbitals will get higher energy than Eg orbitals in tetrahedral complexes. Like this, splitting will be takes place. In square planar complexes, in other complexes also, the splitting will be different. First thing, remember, once again I am saying, when there are no ligands around the central atom, the energy of d orbitals is less. When the ligands are coming close to the metal, the energy of d orbitals increases. They will be get excited. They will be get excited. In excited state, when the ligands are coming close to the metal for ion-ion interaction and ion dipole interaction, due to different orientation of these 5 d orbitals, they split into two groups. In octahedral complexes, Eg orbitals will get more energy than T2G orbitals, and in tetrahedral complexes, T2G orbitals will get more energy than Eg orbitals. So let me see now crystal field splitting and CFSE in a octahedral. First, this is another main principle in a crystal field theory. This is another sixth principle also we can say. Sixth principle, because in previous video we have completed 5 principles and 5 postulates, and this is sixth one. This is sixth one. After splitting this one, next electrons arrangement takes place in these orbitals which are present in a d orbitals only, not the electrons of ligands. Remember, electrons never come from the ligands towards d orbitals in crystal field theory, whereas in valence bond theory and before that Werner's theory, what we have seen, ligands donate the electron pairs, that electron pairs come to the d orbitals, the d orbitals will be filled like that we have seen, but here not like that. Ligands do not give any electrons, just they have the interaction with the metal atom. After interacting, after splitting of d orbital into two groups, those electrons present in these d orbitals will be arranged in this only. No electrons come from ligands. Please remember that one. This is crystal field splitting in octahedral complexes like this, tetrahedral complexes like this. Let's discuss separately crystal field splitting in octahedral complexes, crystal field splitting in tetrahedral complexes. Octahedral complex and tetrahedral complex. Now, I am going to explain crystal field splitting and CFSE in octahedral complexes. Octahedral complexes. Crystal field splitting in octahedral complexes. We know in octahedral complexes 6 ligands. 6 ligands. 6 ligands approach central atom. 6 ligands approach central atom. How that 6 ligands approach in central atom means they approach the central atom through the axis. Through the axis means plus x minus x plus y minus y plus z minus z. Two ligands here, two ligands here, and two ligands here. Total 6 ligands. What it means? Suppose myself is central atom. This is the x-axis. One ligand will come through the x-axis from this side. We can say it as plus x, minus x. Opposite axis will be minus x. One ligand will approach like this. Another ligand will approach like this. This will be plus x axis, minus x axis. One ligand, another ligand. First ligand, second ligand. Plus y, minus y, plus y minus y, two ligands, plus z minus z, plus z minus z, like this 6 ligands approach the central atom through the axis plus x minus x plus y minus y plus z minus z. So total 6 ligands approach the central atom. When the ligands approach the central atom through the axis, the orbitals which have the orientation, orbitals which have orientation along axis will be affected more, will be affected more than other orbitals. Those orbitals which have the orientation along the axis will be affected more than other orbitals. Why? Because they are the point charges. The secondary interaction repulsions will be there. So due to primary interactions, the ligands are approaching metal. Due to secondary interaction, this is important role will be played here for d orbital splitting. Secondary interaction will be play more role for d orbital splitting. Please be careful. Primary interaction responsible for approach of the ligands towards the metal atom. Secondary interaction is responsible for splitting of d orbital. So when six ligands approach the central atom through the axis like this, plus x minus x plus y minus y plus z and minus z. So those orbitals which have the orientation along axis will be affected more than other orbitals. Means simply we can say Eg orbitals will be affected more. Eg orbitals will be affected more than T2G orbitals. Why? Because Eg orbitals dx square y square dz square, the two orbitals have orientation along the axis. Therefore, they will be affected more. So, in octahedral complexes, six ligands approach the central atom along the axis. So, Eg orbitals, that is 2d orbitals, dx square y square and dz square, will be affected more than T2g orbitals. Therefore, Eg orbitals will get more energy than T2g orbitals. Eg orbitals will be more affected. The energy difference between these two, if we say, the energy difference between these two, if we say, energy difference between these two, if we say, of course, the energy difference between Eg and T2G, if I say as delta O, O for octahedral, CFSE will be mentioned generally as delta O for octahedral complexes. So, the energy difference between T2G and Eg, this is energy difference between T2G and Eg, if I say delta O, and this we can say it as barycenter, we can say it as barycenter. So from the barycenter, this energy is barycenter, and from here to here the energy difference is delta O. From the barycenter, Eg orbitals have plus 0.6 delta O. 0.6 delta O. You can say it has what? 3 by 5 delta O. 3 by 5 delta O, 0.6. 3 by 5 only, na? 30 by 5 means 5 6 are 30. So like 3 by 5 delta O means from the barycenter it has more energy, which is equal to 0.6 delta O. And T2G orbitals have less energy from the barycenter, amount of 0.4 delta O, or also we can say 2 by 5 delta O, we can say. From the barycenter, zero point 0.4 delta O energy will be less for T2G, 0.6 delta O energy will be more for Eg orbitals in octahedral complexes. In octahedral complexes, once again I am saying, in octahedral complexes, when before octahedral complexes formation, when no ligands are present around the central atom, the d orbitals of central atom will be least in energy. All 5 d orbitals with the equal energy will be present. When the ligands are approaching the central atom due to primary interaction, the energy of d orbitals increases. Up to certain level, they will be contain same energy. Up to barycenter level, they have the same energy. When the ligands are coming very close to the central atom through the axis, why? Because in octahedral complexes, 6 ligands approach the metal atom through the axis like this, then the orbitals which are orientation, which have the orientation along the axis, that is dx square y square and dz square orbitals, that we can say Eg orbitals will be affected more due to secondary interaction. Due to secondary interaction, they will be affected more. Then they two groups split into two groups, that is T2G orbitals will contain less energy from the barycenter than the barycenter, and EG orbitals contain more energy than barycenter. This is barycenter means energy of d orbitals in excited state. In a excited state. So like this, the energy of EG orbitals will be 0.6 delta O is more. For T2G orbitals is 0.4 delta O is less in a crystal field stabilization. Crystal field stabilization. So this is the energy difference between EG and T2G is called crystal field stabilization energy. Here, for the stabilization purpose only, d orbitals are splitting. That's why this delta O, the energy difference between Eg and T2G is called crystal field stabilization energy. Crystal field stabilization energy. Like this, in an octahedral complexes, d orbital will be split. So I hope you understood. Once again, in briefly, I am saying in octahedral complexes, 6 ligands approach central atom through the axis as minus x plus x minus y plus y minus z plus z. Those orbitals which have the orientation along the axis will be affected. Means Eg orbitals will be affected than T2G orbitals. Due to that, from the barycenter, that is in excited state, d orbitals which are in excited state will split into two groups for stabilization. The energy difference between these two groups is called crystal field stabilization energy of octahedral complexes, delta O. Eg orbitals will contain 0.6 more energy than barycenter, and T2G orbitals contain 0.4 less energy than barycenter. So this is crystal field splitting in octahedral complexes. I hope you understood. Next topic, and once again, please take the picture for this, or you can record all these things, or you can write the notes. That depends on you. First, you should know this one. Why splitting is taking place? Only for stabilization. In excited state, orbitals are not stable. When the ligands are approaching the metal, the orbitals with d orbitals in the central atom will be excited. In excited state, they are not stable. For stabilization, they split into two groups. The energy difference between the two groups is called crystal field stabilization energy. For octahedral complexes, we can say crystal field stabilization energy as delta O. Delta O. O for octahedral complexes. So this is crystal field splitting in octahedral complexes. Next thing is, next seventh one or seventh principle is crystal field splitting in a tetrahedral complexes also. Let me see now. Crystal field splitting in a tetrahedral complexes. So let me see crystal field splitting in tetrahedral complex. How it will be there? Tetrahedral complexes. For these two complexes, we need much importance, and then we have to go for another thing. Now, seventh thing is crystal field splitting. Crystal field splitting. Crystal field splitting in a tetrahedral complexes. Tetrahedral complexes. Crystal field splitting in a tetrahedral complexes. How crystal field splitting takes place in a tetrahedral complex? Let us see. First thing, in tetrahedral complex, 4 ligands, not 6, 4 ligands approach the central atom. 4 ligands approach the central atom by primary interaction. Due to primary interaction between metal and ligand, four ligands approach the central atom through through between the axes through between the axes through between the axes AXES, between the axis, not along the axis, like this. Suppose this is the axis, y axis and x axis. Ligands approach like this between the axis, like this. Suppose this is a metal. Ligands approach between the axis, not along the axis. In octahedral complexes, 6 ligands approach the metal along the axis, but here they are approaching between the axis. Due to this one, listen carefully. Suppose if I say this is the energy barrier, this is energy barrier. If no ligands are there around the central atom, these are the d orbitals energy, that is less energy in a central atom in the absence of ligands. If ligands, four ligands itself water may be, if ligands are absent, the energy of d orbitals is least. When these four ligands approach the metal, then energy of these ligands increases. They will be get excitation. So these are the d orbitals energy when ligands approaches. When ligands approaches, the energy of d orbitals will be increased. Here, when the ligands coming close together, then secondary interaction develops. Due to primary interaction, ligands approaching the central atom and the energy of d orbital is increasing. They are getting excited state. When the ligands coming very close to that, then secondary interaction will be appear. Secondary interaction between metal and ligand means repulsion. Repulsion will appear. Due to that repulsion, these 5 d orbital will split into two groups as T2G and EG. I am writing just circles for time being only. So T2G and E. So these are T2G orbitals. Remember, T2G orbitals will contain more energy than EG orbitals, deadly opposite to octahedral complexes. So suppose if I say this is the energy of barycenter, this is called barycenter. Barycenter means from this energy level the splitting is taking place. That's why we can say it as barycenter. And energy difference between T2G and EG, if we say as delta T, T for tetrahedral, and here CFSE of tetrahedral complexes can be represented as delta T, small t, O for octahedral, and T for tetrahedral. The energy difference between T2G and EG as delta T, if we take, the T2G orbitals will contain more energy, which is equal to 0.4 delta T from the barycenter, more energy than barycenter, barycenter energy, or you can say it as 2 by 5 delta T. Why? Because, sorry, 2 by 5 delta T. And from here to here, the energy difference between EG and barycenter is minus 0.6 delta T, or you can say 3 by 5 delta T. 3 by 5 delta T or 0.6 delta T you can take. Delta T. So like this, splitting will be takes place in tetrahedral complex. Opposite to octahedral complex splitting. In octahedral complex is easy getting more energy, T2G getting less energy from the barycenter. But in tetrahedral complexes, T2G will get more energy, Eg will get less energy. Why? Because T2g orbitals will be affected more than Eg orbitals by secondary interaction. Why? Because the ligands very close to T2g orbitals when they are approach the metal. That's why they will be affected more by secondary interaction. That's why they will be split. The energy difference between this T2g and Eg we can say as delta T. So like this, in tetrahedral complexes, crystal field splitting takes place and CFSC of delta T is like this. CFSC of tetrahedral complex is delta T, that is energy difference, and splitting takes place like this. Opposite to octahedral complex. After splitting, electrons arrangement takes place in a d orbitals. Remember, once again I am saying, in the previous video also I told you, electrons never come from the ligands for central atom. Those electrons present in the d orbital, that only present here. Suppose d5 configuration is there for the metal, only 5 electrons. D4 configuration is there for the metal, 4 electrons. D8 configuration is there, 8 electrons only will be arranged in these orbitals. Never comes, the electrons never come from the ligands. Why? Because here splitting is taking place by secondary interaction, ligands approaching the central metal atom by primary interaction. Primary interaction means attraction, secondary interaction means repulsion. Due to that repulsion only d orbital is splitting here. Due to secondary interaction only d orbital splitting taking place in octahedral complexes as well as in tetrahedral complexes. And in next video, let we see crystal field splitting in square planar complexes and some more complicated level. Let we go for. I hope you understood how the crystal field splitting takes place in tetrahedral complexes and how the crystal field splitting takes place in octahedral complexes you have observed. Before this video, before the first video of to this video, we have main principles of crystal field theory. After watching that video, then go for this one. Before watching, without watching of that video, if you go this one, you cannot understand a single word from this video. So once again I'm saying, for advanced purpose, mains purpose, need purpose, I'm going in depth. I'm going in depth. Easy students, easy level students also can understand. For that ability, in that way only I'm explaining. So please be careful. This is crystal field theory. Crystal field splitting in octahedral complexes as well as in tetrahedral complexes. In next video, let's go for next point, that is crystal field splitting square planar complexes and electrons filling and calculation of crystal field split CFSC for octahedral complexes, CFSC for tetrahedral complexes. All these things let me see in next video. Thank you.